our objective here is to show the relationship between pressure and volume using Boyle's law. So Boyle's law demonstration, commonly the bell jar demonstration, demonstrates how pressure and volume are inversely related to each other, and what is being held constant or not changing is temperature, which means temperature is not a factor. So let's look at this little video clip. What you'll notice is she places the marshmallows on the bell jar, and then there's a vacuum pump here that sucks the air out of the bell jar, which decreases the pressure inside the jar, causing the volume of the marshmallows to increase, do the opposite. As she lets the air back in, the pressure increases, which decreases the volume of the marshmallows. So, what happens inside the bell jar? When the machine was turned on, air particles were sucked out or removed from the inside of the jar, which caused a decrease in the pressure inside of the jar. When the pressure went down, the marshmallow's volume increased. So, Boyle's law is a relationship between pressure and volume. At constant temperature, which means temperature is not a factor, volume and pressure are inversely related. They do the opposite of one another. So as you take the pressure and you increase it, it's going to cause the volume to decrease, do the opposite. Consider this equation down here. Because temperature is constant, that means we could ignore the temperature in the equation because it's not a factor. So if we're just focused on pressure and volume, notice our equation is pressure times volume 1 equals pressure times volume 2. So when you increase pressure, it's going to cause volume to decrease. Or opposite of that, if you decrease pressure, it's going to cause volume to increase, and that is essentially Boyle's law. So show what Boyle's law will look like on a graph. So here you can see as the pressure gets increased, the volume gets decreased, and vice versa. And so it causes us to have kind of a curve. And so we get a hyperbola, which is half of a parabola. So it's a volume versus pressure graph, and then the graph is showing that as the pressure goes down, the volume goes up. And as the volume goes down, the pressure goes up. So now we're going to work on some calculations. First, this is number 1. This is the general equation we'll use for all calculations in this unit. However, if something is constant, then that means you ignore it in the equation. So, for example, when we read this problem, if you move 5 atmospheres of gas from a container that is 2 liters, notice this is the first pressure we come to, so we're going to call this pressure 1. And then as we continue to read, this is the first volume we come to, so we'll call that V1. Then here's the second volume, so we're going to call this V2. And then it says what will be the new pressure. So P2 is what we don't know or what we want to know, and I'm going to circle it so that I recognize that that's what I'm solving for. Notice that they did not give us temperature anywhere in the problem, which is how I know that I can ignore the temperature in the equation that was given to me. So now we can take our numbers given to us in the problem and plug them in here. So P1 is 5.0 atmospheres times V1 is 2.0 liters equals P2 is what I'm solving for, and then V2 is 6.0 liters. Now, if you prefer, you can mark P2 as X if that makes it easier for you to solve the problem, right? So now we're going to leave it as it is. Algebraically, you're solving for X, but really, we're going to kind of do what we did when we cross-multiplied. You're going to start multiplying not on the side with the X, but on the other side of the equal sign. So it's going to be 5 times 2, and then anything on this side with the X, we're going to divide by it. So then I'm going to hit divided by 6, and that's going to give me 1.67. So X equals 1.67. And because that's our new pressure, whatever P1's unit was, which was atmospheres, is going to be P2's unit. So this is 1.67 atmospheres. Number 2, if you change the pressure of a gas from 2 to 4 atmospheres, so notice that we are doubling our gas pressure. So pressure is times 2. What must happen to the volume if everything else stays the same? And so because volume and pressure have an inverse relationship, that means that when you increase the pressure by 2, we're going to decrease the volume by 2. So the volume will be cut in half, or times 1/2. So if it's pressure times 2, then it's going to be volume times 1/2. Okay, and then number 3, here is our equation. Okay, if something's constant, we ignore it. So let's see what we have in our equation. A gas with a volume of, that's the first volume you come to, so we're going to label that V1. Is at a pressure of, this is our first pressure, so we're going to call that P1. It's allowed to expand to a volume of, there's the second volume we've come to, that's V2. What is the pressure? So we're trying to solve for P2 if in the container the temperature is constant. So because temperature is constant, that means that we can ignore it and we do not need to use it in our equation. So we'll just kind of cancel it out. So now I can set up my calculation where I'm going to plug in the values. P1 is 205 kilopascals. V1 is 4.00 liters equals, I don't know P2, I'm going to go ahead and call that X. And then V2 is 12.0 liters. Now we are going to multiply and then divide. Don't start multiplying on the side with the X. We'll multiply on this side first. So it'll be 205 times 4.00. And then anything on the side associated with the X, we're going to divide by it. So divided by 12, and that's going to give us X equals 68.3. And then notice that we are solving for P2, so whatever the unit is for P1, that's the unit on my answer, which is kilopascals.